So let's talk a little bit about Newton's second law. This is the like the heart of dynamics. And so Newton's second law is simply that if there is an acceleration on an object, then the acceleration is determined by the net force on the object divided by the mass. And this is the way it'll look on your equation sheet. You may be familiar with it as like force equals mass times acceleration. That's just this equation rearranged. The acceleration is the result of a net force. So if I have some unbalanced force, we're going to have some acceleration on the object. And this is Newton's second law. And then we can break that out into components, and we can say, well, the acceleration in the x direction will be the net force in the x direction divided by the mass, and the acceleration in the y direction would be the net force in the y divided by the mass. So similar to what we've been doing, finding net force in your component form, and you can then divide that by the mass, and that will tell you the acceleration. And the big idea here is that we're going to have to be able to move from kinematics into dynamics. And the thing that links these two together is acceleration. So you may be given forces and such, and you'll determine the acceleration to then get the position or velocity or time, or you may be given the time and velocity and stuff and have to determine the acceleration and then use the force or the mass to get the forces. So anyway, you move back and forth between these based on what you're given. So over here you have velocity, you have time, you have the displacement. If you're given any of these, you're going to determine the acceleration, and then you could find the net force or the mass, just depending on what it is. And that's as complicated as it's going to get conceptually. Now the problems themselves will get a little might get a little funky, but it's really not that big of a deal. So let's try a few problems, or at least some examples. So say we had a I don't know, a 2 kilogram box being pushed with a force of, we'll say it's frictionless, say a force of 10 newtons. The question is, what's the acceleration? So I only have a force in one direction. Well, we have force of gravity and the normal, but those wash. Those will be equal to each other. So we don't care about the y direction. It's just this x direction. So the acceleration in the x direction is going to be the net force in the x direction divided by the mass. And so it'd simply be 10 divided by 2. 10 newtons divided by 2 kilograms, which gives me 5 meters per second squared. So that's in one dimension. You know, if I had, so suppose that I did have some friction. Let me get a different color here. So suppose I had some friction acting backwards. So say we had a friction force of, I don't know, 2 newtons. Well, then my acceleration in the x then would change. It would be, of course, the net force in the x divided by the mass, which would be 10 newtons plus the negative 2 divided by 2. So we would get, that's 8 divided by 2, so it would be 4 meters per second squared. And that makes sense. My acceleration would decrease because my net force is less. All right, let's do how about a kinematics one? Let's see if we can make up one from kinematics. So suppose you're going at, suppose a ball is falling. Yeah, let's do a ball. A ball falls off a building and falls into like a bush. Yeah. Okay, so right when the ball strikes the bush, its velocity is, say, 6 meters per second. And over some distance, and we'll call that distance, let's say, I don't know, half meter, 0.5 meters, it stops. What was the force, what was the net force that stopped the ball? So here we can see we're given velocity and distance, so that's kinematics, and we're asked a question about dynamics. So we're going to have to determine acceleration to go between these things. So thinking about this, let's see, I have an initial velocity of 6 meters per second, and it stops, so my final velocity is going to be 0 meters per second. And then I have a distance it traveled. Delta x is 0.5 meters. So what I want to know is what's the acceleration. And notice there's no time. So we're going to have to use this equation. And I'm just going to put delta x. Your equation says xf, or x minus x naught. But that's just change in position. I know how far it went in total, so I don't care about the individual x's. And so I can see my final velocity is going to be 0, so that goes away. So if I move this over, I get negative v naught squared equals 2 times delta x, and then divide by delta x, so negative v naught squared divided by delta x equals the, oops, I forgot an a in there. That's acceleration. There's an a. So divided by 2 delta x equals the acceleration. And I'm going to say x, but you know it's in the y direction. It doesn't matter. It's just a displacement. I could just say that, you know, x is in this direction and y is in this direction. Anyway, you'd probably do it in y. That's fine. All right. So what I can see here without plugging in any numbers is that it's going to be a negative. And so negative acceleration, does that make sense? Well, it's stopping. So I can see that since I defined it positive, I actually defined it positive, so this is negative x, that this is positive direction. So yes, it's slowing down, so I have negative acceleration. So this would be negative 6 squared divided by 2 times 0.5. And 2 times 0.5 is 1, so it's negative 36. So my acceleration for this object is going to be negative 36 meters per second squared. All right, so to get the mass, then we go into dynamics, and that's going to be your net force divided by mass, or your net force is going to be the acceleration times the mass. So we would need to know the mass, and we would get 36 times the mass. I don't know, we'll say 2. All right, so we get a negative 72 Newton force. So the force, the net force, was acting upward because of the way that we defined it. Again, if you flip everything and you know the sign, don't stress too much about it. All right, and it could work the same going from dynamics into kinematics. You could just determine let me get a new page open. The acceleration, and then use kinematics for that. So suppose you're pushing a crate. Let's say there is friction. So you have some friction force coming backwards. And we'll say it's kinetic friction. But you're applying a force to it of, I don't know. You're just applying a force, okay? Let's say that. You're applying a force of 20 newtons. The mass of this thing is, let's say, 10 kilograms. Okay, so you're applying the force, and it's moving at constant velocity. Constant velocity. And then the question is, after you're going to take off this force, so you stop the force, how far does it go? So how far does the box move with no force when the force is 0? So you take away the force, how far is it going to go? Okay? So let's think about this. First we need to determine the acceleration. The acceleration is going to be the net force divided by the mass. But I said that it's constant velocity. So we know that the net force is the same. So we know that the force of kinetic friction is also 20 newtons because the net force equals 0. So force plus the friction is 0. So the force equals the inverse of the kinetic. Therefore, the kinetic friction force also equals 20 newtons. It's just in the negative direction. Okay, so now we can use kinematics. Yeah. Oh, wait, yeah. Okay, so we remove this. We remove this force. And so this is the only force that's left. So the acceleration of it after we remove it, this is to begin with. So after we remove it, the net force is just the kinetic friction force divided by the mass. So the acceleration is going to be the negative 20 newtons divided by the mass of the object, which is 10 kilograms. So we get an acceleration of negative 2 meters per second squared. All right, so now we have the acceleration in the x direction. Now we can use kinematics, and we want to know the distance, and I have acceleration. Don't have velocity, but we know that it's constant. I don't know. Let's see if we can figure this out. If not, we can just make up some numbers. So, oh, you know what we can do? We can use this one. So x is x naught plus v x naught t. No, that ain't going to work because we don't have the time. So v is v naught plus a t. Again, I don't have time, so we got to use vf squared is v naught squared plus 2a delta x. I'm trying to find the delta x. I don't know the initial speed. So let's say it's moving at a constant velocity of, I don't know, 3 meters per second, just for sakes of finishing this problem. The final velocity is going to be 0. And then we have the initial velocity squared plus 2 times the acceleration times delta x. So again, I'll just subtract this over, so negative v naught squared, and then I'm going to divide by the 2a, and that would be my change of position. Yeah, you can just plug in the numbers. And so this is basically what it boils down to. It's using Newton's second law. You're going to have to determine net force from force diagrams. You're also going to have to draw force diagrams, figure out the force, go back and forth between kinematics and dynamics. I know it seems like a lot. It just takes some practice, and it won't be that bad.